Hey everybody, these remainder problems involving exponentials with really, really large exponents are very, very common. Normally it's just one, I think, on a lot of these competitions. Here we have four of them summed together. Now we can use the fact, and I'll show this in just a minute, 11 raised to the fourth power. It's not too hard to show that that's congruent to 1 mod 16. Again, we'll hint around why that's true in a minute, but that just means if you subtract 1 from 11 to the fourth, you get a multiple of 16, or when you divide 16 into 11 to the fourth, you get a remainder of 1. Okay, now, so let's take a look at the approach I chose here. And by the way, let me just, while I have this here, this is equal to, exponentially at least, you could say 11 to the fourth, and we're using that for obvious reasons. 11 to the fourth raised to the what do we need? 255? 506? Yeah, 506. 4 times 506 is 2024, and then this is just times 11, right? But you see how this would be congruent to 11? Just congruent to 11. See, since this piece right here is just 1, we can replace it with 1 from a modular arithmetic perspective. And you already know that this would be congruent to 11 mod 16, right? You do something similar with this term, and this term, right? But I'm going to do something a little more general that I saw in one of Wei Tan's videos. Now, I wrote this down as a fact. This is pretty easy to see. I'll just do one of the computations for you. 11 squared is equal to 121. But that's equal to what, 7 times 16? Yeah, this is equal to 7 times 16 plus 9. 16 being the modulus here. So see, this 9 that you see right here is this 9 that you see right here. In a similar fashion, you can compute. And once you've computed this, you can just multiply this by 11. That would give you 99, and that's congruent to 3 since 8 times 12 is 96. Or what? 6 times 16 is 96, excuse me. But the key aspect of all this is we get down to this 11 to the fourth is congruent to 1. When you multiply by 11, you get 33. 2 times 16 is 32, so you leave this remainder of 1. Now, y'all, this 4 is called the order, okay, of 11. Okay, it's called the order. It's called the order of 11 mod 16. Okay? But a nice thing happens here. You can see what happens once you get to 1, you get this cyclic nature here. You can just see the pattern here, folks. You see how the 11s appear in the first column, the 9s appear in the second column, and so on, okay? So that's the nice thing about discovering the order of an integer is that you'll get a periodicity associated with that. The period is 4, okay? Now, and let me put, just to be for emphasis here, a vertical ellipse. Okay, I love ellipses, but this would go on and on and on, and so I'm going to make a bold claim here. Mod 16, 11 to the k, 11 to the k plus 1, 11 to the k plus 2. That's 4 consecutive as far as the exponents go. They fall within this set 11, 9, 3, and 1, and that's it. And notice it doesn't have to be, it's a wraparound. You could start here at 11 to the fourth, do 11 to the fifth, all the way to 11 to the seventh, and they're going to be the elements in this set, right? It's not just the rows. You can wrap around any way you want. At 4 in a row, you're always going to fall. Now, you could prove this. I've seen Michael Penn prove these kind of things. You can prove this deductively rather than inductively, kind of like I've done here, by just assuming that this isn't true, and that you would get a contradiction on the order. You would find an element that had a smaller order than 4, I believe is how the proof would go deductively. But we won't worry about that now. Now, what we have right here, this would be the case right here, k equals 2025 right here. And you don't even have to know what order to go in here. You know what I mean? I think this is in the same order. But you just know that since the exponents are 4 successive natural numbers, that this is going to be congruent And again, the order 11, 9, 3, 1 is not important. Sets were created to get rid of the notion of order, I think. But this is congruent to 11. And I'm not saying these line up. They don't. You don't have to worry about that, okay? 9, 3, 1. Okay. Whoops. Not parentheses. Let me erase that. Okay, let me get back here to, okay, this will be plus, oops, I got a bigger one there, that's okay, we'll live with it. Plus 1 equals to, what is that, 20, 24? Okay, but notice that that is congruent to 8. Okay, guys, if those of you, I mean, that modular arithmetic is useful because it's sometimes called remainder arithmetic. It puts all the integers in the same equivalence class that have the same remainder based on whatever modulus you're dealing with. So this is our answer, 8. All right, and let's come up here and put that the remainder is 8. Okay. And again, folks, you could even do this directly, I think, but you'd be left with a lot. You could factor out 11 to the 2025th and see what you had, but you'd end up with a large parenthetical quantity. You'd still have to divide that by 16 and see what kind of remainder you got. But it would be 8, I can assure you that. So, all right, that's the answer to the problem, folks. And I kind of like this idea of talking about the order and then making a statement like this, which is clearly true. Once you run into 1, everything's going to start repeating with the periodicity of that exponent. And then you get this claim right here, which, again, I did not prove anything deductively, really. It's more of an inductive sort of thing. And then you get to this position right here where it leaves the result in no doubt. Now, and again, I'd like to, again, you could have done each one of these individually like I did right up here, where I showed you 11 to the 4th is congruent to 1, and then we used this, you know. But think about the magnitude of these numbers. Just think about, even a number like 11 to the 10th is already too hard to manage, right? So these numbers literally are unpronounceable, just unfathomably magnitude numbers, you know. And so this modular arithmetic is a cool way to minimize the effects of large magnitude numbers, in a manner of speaking. Even this part right here of going, you don't have to keep up with how big 11 squared is once you know it's congruent to 9. Same thing with 11 cubed. You don't care how big it is once you know it's congruent to 3. So that's the value of modular. That's one of the valuable things about modular arithmetic, that you come up with a symbol that's more or less the same thing as equality when you're dealing with the remainders instead of the number itself. Okay, that is all. Thanks for viewing.